I mentioned in the last lecture we looked at applications, and I introduced these funny looking co-inductive records as a means to an end, and I thought it might be worth stepping back from that a bit and getting a better look at what was going on. So this lecture is going to be comparing inductive types and co-inductive types, and just getting more of a feel for that distinction. And I'm going to try and keep the examples nice and simple. So I want to start with good old lists are a typical example of an inductive data type. Built up from a base case, nil, by a step constructor, cons, and in Agda, unlike in Haskell, lists have the property of being finite. You know that when you write a recursive function over lists, you keep peeling off the conses, that you will eventually reach the nil. So you can do things like measure the length of a list. So I want to sort of look at the structure of lists. So first of all, if I wanted to make a general purpose constructor for lists, so we've got a nil and a cons. If I wanted to roll them up into one general purpose make any sort of list function, I would need to give it an input that had enough information to say, first of all, whether we are making a nil or a cons, and then if we're making a nil, we know how to make nil. If we're making a cons, we need to know what pieces to make it from. So in general, I have to give either enough information to make nil or enough information to make cons. So let's just do this. In general, I either have in left of empty tuple, or in right of a head and a tail, and then I can pack up the result. If we go left, that means make a nil. If we go right, that means make a cons from the pieces that were given. So what we have is packed up as a single thing both constructors. This is the general how to make lists thing. We can think about what sort of a thing it is in a moment. And then you might remember from Haskell there was a function called fold_r. Well, this is a slightly different version of fold_r, but only slightly. The key thing, rather than giving a nil case and a cons case, I'm giving one thing here, which says, if I'm trying to make a t, and I know how to make a t given either an element of 1 or a pair of an x and a t. So let's just see how that works. I look at the, so that's saying I know how to make t's according to the same way that I know how to make lists. You can see I've got t here wherever this had list x. So what happens if I get a nil, I've got to make a t. My only way to make a t is to use this thing which I've called alg for some reason. And now I've got to say which input I'm going to give to t. And actually, I don't really have a choice about which one to pick. I've got to say, in this base case, I've got to say go left. So choose the base case for making t's. And then it won't surprise you to learn that, again, in the step case, I've got to find a way to make a t, and the only way to do it is using alg. And if I ask for a list of possible ways to fill in the argument of alg, it gives me a bunch of things, and I like the look of number 2. So what I'm going to say is, this time in the step case, I'm going to go right, so I have to give a pair of an x and a t. I'm going to give the x that came in from the head of the list, and I'm going to get my t by turning x's into a t recursively. So what I'm saying is, whichever strategy was used to make the list, deploy the corresponding strategy to make the t that is being computed from the list. So build up the t the same way the list is built up. And that is, in general, how we build recursive functions over inductive data types. We say how to build up the output following the same construction pattern that was used to build up the input in the first place. So operationally, it's take the input apart, seeing how it was built, and then echo that to build up the output from the recursive pieces. So what is this?
The font up a wee bit more.
Sorry?
The font up.
This alg thing, it's not algorithm, but it's not far off. It's algebra, which was, of course, a word invented by Mr. Algorithm. Al-Khwarizmi's algebra is the method of balancing, the method of doing the same thing to both sides of an equation to keep it true and deriving things that way. But in our world, an algebra is a way of computing values from some form, from some container for values. It's a way of saying, here's a way of interpreting some lump of syntax. So our algebra interprets in lefts and in rights as instructions for building a T. So you can think of it as a way of sort of giving meaning to symbols. Okay. So actually, what I want to do, having lined this up, just to make it doubly clear, we're seeing this formula 1 plus x times something showing up a lot. So let me just abstract that out. Now what's just happened? Oh yeah, there should be an x there. So this list f thing has a parameter x that stands for the element type, and then the crucial other parameter t you can think of as meaning substructures. And this explains the ways in which you can build a list-like superstructure from the given notion of substructure T. That's to say, you either build a nil-like thing, or you build a cons-like thing with an X at the head and a T at the tail. So make list says, if I have a list F whose substructures are already lists, then I can finish the job and build a whole list. Whereas this thing says, if I know how to make a T from a list-like thing whose substructures are already T's, then I can turn a whole list into a T. So these things that look like f of t arrow t, let me actually stick in an extra set of brackets, even though Agda doesn't need them, just to emphasize the point. And I'm not going to do all the proofs, but I am going to point this much out. What's the F for? Well, it's for functor. You can see I'm going to write the map operator for list f of x. If we've got a list-like thing with t substructures and we want a list-like thing with u substructures, all we need is to be able to turn t's into u's. So what happens? We look at what we've got. So either we get a nil-like thing coming in which case we better give a nil-like thing going out, or we've got a cons-like thing coming in, but the tail is a t, in which case, what do we need to give out? Well, we need to give out a u in the tail position. We've got a t, and we've got a function that turns t's into u's. So this really means do G to all the substructures, even if there aren't any. Right. In this case, there aren't any substructures, so we get back exactly what we put in. And in the step case, there's one substructure, so it gets hit with G. So what's going on here, what we've isolated, is the functor that describes how you build lists from sublists. You either give a nil, or you pack up a sublist with a head. Okay, and what we're saying, so what an algebra does is, given such a functor, is to say, given a structure full of substructures, given kind of a node full of substructures, give me the whole structure, give me the whole thing. So we're either saying, so here it's given a node full of sublists, give me a list, and here we're saying, if we know how to turn a node full of t's into a t, then we can turn a list into a t. So one obvious thing to consider is, given that fold works with any algebra and make list is a particular algebra, what happens if we use make list as the algebra in a fold. What do you think happens?
Nested lists.
You're overthinking it. So fold says build up the output the same way the input was built, and but using this algebra instead, and then we're giving it the algebra for building lists in the first place. So build up this output list using the same algebra for building lists as was used to build the input list. What's going to happen?
The same list?
Nothing, exactly. So if we look at x1, we get out exactly 1, 2, 3. So we're saying if you plug in the algebra for building up the data in the first place and use that to process the data, nothing happens, which is, at least to some extent, reassuring. Let's do something with a different algebra, just to show that we can compute the length of a list this way. So you'd usually write this recursively, and all we're doing is bottling that recursion pattern. So what do I have to give here? To compute a number from a list, I have to give an algebra. An algebra, we say that the value type that we're working with is called the carrier of the algebra. It's the actual underlying notion of value that we're building. So what we're saying is, how do we give an interpretation of nil and cons for numerical values? I really have to give a function that. Nope. Yeah, what am I playing now? I'm going to have to do some local pattern matching. Okay. So you can see I've got a Z, which tells me whether the input is built nil style or cons style. So I pattern match on that. And then here, if I look at the X, I get no more information. So if the list was built up nil style, we should probably say that the length that we give back is 0. Otherwise, what have we got? We've got the element X that's at the head of the list, and instead of having the tail of the list, we've got the number it turned into. So we're basically saying, look, imagine we've already computed the length of the list. So the tail of the list has been turned into its length. How would we give back the length of the whole list? Well, we take the successor of n. So I could compute the length of example 1, and that would be 3. Thank goodness for that. So we're saying, here's an algebra, which isn't the algebra for building lists. It's an algebra for building numbers according to the same patterns that lists are built from, which is enough information to explain how to turn a list into a number. You think about all the programs you've ever written that do stuff with lists. Loads of them are like this. Think about when you learn to build, let's say, a binary search tree. You explained how to give the empty binary search tree and how to insert a number into a binary search tree to get a new binary search tree. you were implementing an algebra for list F with carrier binary search tree. You're saying, I need to know exactly how to build up binary search trees in the same patterns that lists are built up. Yeah?
And is it the rest of the list, or is it just an actual number?
No, let's just check the types again. If you look in the context, the n is already a natural number. So that's to say, in this recursion scheme, when you get your hands on the bits, the components coming into the algebra, the sublists have already been turned into whatever you were computing from them. Yeah? So the tail has already been processed, and what you have in its place is the length of the tail. So the right thing to do is to take the successor of the length of the tail. Okay. So I could go on, but what I want to do is to turn the world around. The notion of a co-list, which is much closer to what Haskell calls a list, is instead of being something that lets you build it up as a nil or a cons, it's something that lets you ask it, are you a nil or a cons? So it's a record with this co-inductive tag that allows me to write a recursive definition, which says, it doesn't really matter what a co-list is, as long as it implements this piece of functionality, which is often called force. Now, when we force it to tell us, it will tell us whether it's a nil or a cons. And if it's a cons, it will tell us what its head is and what its tail is. So rather than saying lists are just the things built up from nil and cons, we're saying co-lists are any old thing which will answer this question, are you a nil or a cons? So let's check some stuff out. First of all, let's show that there is a nil constructor and a cons constructor that build co-lists the way we're used to lists being built. Here you see something slightly funny. We saw it last time. I think we've seen it a couple of times before, but let's look at it properly. One way to define records, and it's a good way to define co-inductive records in AGDA, is to explain component by component what they are. And it looks a little bit weird. You can see here, our goal is to make a co-list X. And one way to do that, well, the way to do that is to explain, right, remember, we're not promising anything other than we will deliver this behavior. So the way to define a co-list is to explain how we deliver that behavior. So I'm going to do, I haven't got finger cam on, but I'll tell you what I'm doing. Control C, like I'm making a case analysis, but down here it says, pattern variables to case, brackets, empty for split on result. What is this split on result business? Well, I'll leave it empty and I'll hit return. And what happens is that the left-hand side gets wrapped by the field projection. And if there were multiple fields, we'd split into multiple lines, one for each field. So here we're saying, instead of the usual pattern matching, which splits into different lines corresponding to each case for a possible input, each choice there was, we get multiple lines for each component we have to build for the output. But it's still splitting a problem into sub-problems. Normally, or in the past, we would have built up a record on the right-hand side, giving each field of the record. But here you can do it by splitting it into sub-problems. The projections appear on the left-hand side. So we're saying, how do you force this empty colist? Or rather, how do you say what the empty colist is? You do it by explaining how to force it. Okay, and you can see that the type of the goal has now changed to the output type of the force projection. We have to explain what this thing gives back. It's supposed to be the empty colist, so we're going to choose to go in left and give the nil-like thing. Same deal happens for the cons. How do we define the step case of a colist? Well, we do it by explaining how to force it. And this time we say, if you force me to say whether I'm a nil or a cons, I'm going to say I'm a cons, and then I have to give a pair of a head and the colist that's the tail. Well, that's going to be x's. All of this being forced to say whether you're a this or a that reminds me of being a kid in Belfast. But not entirely pleasantly. Yeah, so one thing we could do while we're about it is simply to note that the type of force gives back a list fx, and again I'll put that in an unnecessary extra set of parentheses. It gives back a list node structure with colists as its substructures. So that's to say, when we force a colist, it must show us its top layer. So it produces those top layers on demand. And then let's look at the general way of building colists. So the general way we do it, I can see, let's make this substitution. Too many parens. So this says, let's suppose we've got some type S. You can think of S as the type of seeds, or states if you really like, but I think of them as seeds. Unfold R tells you how to grow a colist from a seed. To grow a colist from a seed, you need to know how to take a seed and compute from it the top layer of a list-like structure. And anywhere you might need a sublist, a substructure, you're going to have a seed from which to grow that. So if we have that information, we ought to be able to grow a colist on demand. So let's see how to do that. We're supposed to be manufacturing a colist, and the only way to do that is to explain how we will respond when we're forced to. So we have to say, okay, what happens when we force this thing? And now I have to give a node structure with colists as substructures. And fine, what I'm going to do, I don't know yet whether I should give back the nil structure or the con structure. But if I get hold of the result of applying this coalg thing to S, that should tell me at least what I need to give back for the top layer. That's its job. So I look at what comes back. And I say, okay, coalg says go left. That means I'm going to go left. The thing that says how to proceed from, how to carry on given seed S says it's time to stop. So we say, yes, okay, fine, we'll stop, we'll give back the nil. If the coalgebra says your first step is to build the cons, then we shall build the cons. And we have to give back the head and the tail. Unfortunately, we were told what to put in the head position, and now we have to explain what to put in the tail position. Fortunately for us, we don't know the whole co-list that we want to put here, but we do know the seed from which we can grow it. So I can say unfold our coalg S prime. And it's happy. This is the mechanism for growing a co-list on demand every time we ask it, are you nil or cons? It looks at the seed, feeds it into coalg, and that tells it how to answer the question. Gives just enough information to answer that top level question, are you a nil or a cons? Okay, so funnily enough, coalg is short for coalgebra. So what do we have? Maybe if I do a vertical split, let's get unfold R in one place, and fold R in another place. Fold R takes an algebra, a way of taking layers full of T's and giving back a single T. And that enables us to produce a T from a list. The coalgebra has the functor on the other side of the arrow. It says, I know how to grow an S into a list layer full of S's. And that's enough information on demand to grow a whole co-list from an S. So it's the same deal. And you'll notice that, well, what happened here and what happened, compare what happens in this with clause with the definition of map. It's pretty similar. So let's just have a cautionary tale. What I'd like to say is first of all, apply coalg to S and then post-process its substructures somehow. And that's fine. All I have to do now, given that the substructures coming out of coalg, the substructures are seeds, I have to explain how to turn each seed into a coalist. But isn't that what we were doing in the first place? And at this point, the termination checker is too stupid to see why this recursive call is okay. Or rather, in this case, it's the, strictly speaking, it's annoying that it calls it termination checking, because it's not termination that we're checking. We're checking what the dual notion to termination. So termination is that the program eventually stops, and that's guaranteed by the fact that when we start with inductive data, we can't keep taking it apart forever. It's built up from base cases in finitely many steps, so we can't keep taking it apart forever. The corresponding notion for co-inductive data is productivity. Productivity is the guarantee that we can always give out the next bit on demand. So we need to show that this unfold R process will always give out the next bit on demand. And it's not clear to Agda's productivity checker that listf will use this in a way that guarantees productivity. So this is not the first time, and it won't be the last time, that in order to make that explanation clear to Agda, that what we basically had to do to get the program that was accepted, what did we do here? We got the result of coalg S, and then we did exactly the same calculation as listf to it. We inlined listf. And then Agda was happy. So that's the situation where Agda's not going to look inside the definition of listf to see that it doesn't do any bad stuff with this function. But if we inline it for ourselves, Agda will see that everything's fine. So that's a thing that often happens. Later I'll show you how to put that problem into one tiny box and essentially solve it once. So why is this okay? This is okay because the recursive use of unfold R occurs under constructors on the right-hand side. That's to say, Agda can see that we're definitely pushing out some data before the next phase of unfolding happens. There's otherwise what? I can show some bad examples in a moment. Right. So one thing we should note is that force itself is a coalgebra. It's the coalgebra that tells you how to make the top layer of a coalist from a coalist. It's just make a coalist make a coalist top layer by showing me your top layer. And funnily enough, if you feed in a coalist and you unfold R with force as the coalgebra, well, what are we expecting? Is it the same thing? Well, no, that's the point. It just sits there. The thing about co-inductive data structures is that they are unfolded only on demand. So this thing is sitting here saying, well, I'm the thing that's ready to build you a co-list by repeatedly forcing this thing. I'm ready, but what? It's just there being ready. We haven't actually asked it any questions yet. It's not going to spit out data until we kick it. So let's kick it. I'll do this one first. Right. So we could say, for any co-list, we can say, what are your first n elements? Give me the first n, or fewer. Remember take in Haskell. That's what this is. Take the first n or fewer elements from this co-list and give it back as a list. So let's see what happens. We need to first of all look at how many we want to take. If we don't want to take any elements, then we don't need to wake up this co-list. We already know we want to give back the empty list. If we want to take at least one element, then we'd better force the top layer of the co-list. What just happened there? I forgot to say width. Okay, so we asked this co-list, are you nil or cons? And it either says, I'm nil, in which case, sorry, you're not going to get successor of n elements out of this co-list. You'll have to make do with none. Or we've got a cons with a head and a tail, in which case we can say, well, we'll definitely give back the x, and we'll take the n-fold prefix of x's prime. Yep?
So the way I see it now, why do we have to go through core list to go back to list of x? Why don't we just have an unfold for list?
Well,
What's the point?
so the problem with unfold for lists is that we need to know that it stops. Lists have to be finite. So we're guaranteeing that it's finite by giving a bound on how long the list can be. So this program makes sense because it's decreasing on the number. The list, as we'll see in a moment, might not, the co-list might never end. Let's just check that if we ask for prefix for the first 3 elements of example 2, we get something sensible. Example 2 prime asks for the first 3 elements of that co-list. So that basically says, force that co-list all the way down to the 3rd layer and extract the elements, and we get our 1, 2, 3. So it's designed so that, well, I mean, actually just time tells you that in the course of running a program for a finite amount of time, only finitely many forcings can happen, because there's only a finite amount of time for them to happen in. And correspondingly, as long as each force is guaranteed to deliver just enough to satisfy that request, the potentially infinite structures that we build won't, as long as they don't unfold unnecessarily. If they just unfold on demand, everything will be fine. So let's have an example just to show that we can build co-lists that go on forever. So here we have repeat is going to build a co-list X from an X. So this element type is going to be the seed. What do I have to do? I have to grow from a single X one list layer whose substructures are also X's. Well, I think I can manage that. Okay. Now I have to say, is it a nil or a cons? I'm going to say, it's a cons. Why did it fail to give that? Because that's weird. Now I've got to say, what's the head of the list? Well, I don't have much choice. X. And now I have to say, what's the seed from which I'm going to grow the tail of the list? Well, that's also X. So whenever we kick repeat, it will say, I'm a cons, here's the head, and then the tail is keeping on going, ready to do that some more. For as long as we keep kicking, as long as we keep forcing it, it will spit out the same value. So let's see what happens. If we say, what's the result of prefix 3 of repeat? I've got not very many types in this file. Repeat 0. It gives me 3 zeros. If I say, what's the result of taking the prefix 42 elements of repeat 0, I get, I hope there are 42 of those. Tell you what, let's find out. Oops. What's the length of the prefix of repeat 42? Sorry, prefix of the 42nd prefix of repeat 0 is what we want. Oh, reassuringly, it's 42, so we did get 42 of them. Right, so what's the point here? We can't make a list that goes on forever like repeat does. So the benefit of being able to, it doesn't really go on forever, that's the point. It goes on for just as long as we ask it to, and since we can't go on asking it to forever, its patience will outlast ours. That's the point. But one thing we sure can't do is measure the length of a co-list. So why can we measure the length of a list? Because we know that sooner or later it stops. And so that's an extra demand for making lists than for making co-lists. For making lists, it's not enough to know that you can tell the difference between a nil and a cons. You certainly have that, but you also have to know that it won't keep on going saying cons forever, that it will eventually stop with a nil. That's the extra thing that makes lists special. But correspondingly, so there are things that have that property that will answer the question, are you a nil or a cons, that don't have the property that they eventually stop. Repeat is one of them. So there are more co-lists than there are lists, but you can do more stuff. You can compute more stuff from lists because you know something more about them. Yeah? So there are more useful programs with with lists as inputs because you can exploit the property that the input will stop. And there are more useful programs with co-lists as outputs because all you have to do is answer the nil or cons question on demand. But the two are built in dual ways. We build lists from a list algebra and we compute from them by giving some other algebra for list structures. We unpack co-lists with a list co-algebra and we compute co-lists from any old list co-algebra, growing them from a seed. So these are in the mirror images of each other. Okay, I should stop there and catch a train.